All right, let's dive right into this. Welcome to today's explainer. We're embarking on a really fascinating, centuries-long evolutionary quest today. We are looking at the evolution of manufacturing automation. It's this wild journey that literally takes us from the very first water-powered mills all the way to the hyperconnected, cloud-based factories of tomorrow. To truly appreciate where we are today, we kind of have to step back and ask, how do factories produce millions of perfectly identical products without any human hands involved? Think about early manual manufacturing for a second. Yes, it was incredibly skilled, but man, it was also unbelievably slow, highly susceptible to human error, and just massively expensive. Every single time you needed a new product or part, entire machines had to be painstakingly retooled and adjusted by hand. Just a massive headache. So the answer to that massive historical bottleneck is our ultimate solution: automation. Now, the term itself actually comes from the Greek word automatos, which just means self-acting. In the manufacturing world, automation is basically the process of enabling machines to follow a predetermined sequence of operations with little or absolutely no human intervention. It is the direct answer to those human limitations of speed, fatigue, and inconsistency that we just talked about. So here's our roadmap for this explainer. 1. The drive for automation. 2. Hard versus soft automation. 3. The birth of numerical control. 4. Open and closed-loop systems. And finally, 5. The future of manufacturing. Let's get into it. Section 1. The drive for automation, solving the human problem. Now, this monumental shift away from manual, backbreaking labor obviously didn't happen overnight. Now, what's really interesting about this timeline is the historical pacing here. Things start off pretty slow, and then they absolutely explode. Look at this. Back in 1808, we had sheet metal cards with punched holes controlling the patterns on weaving looms. Then fast forward over a century to 1945, and the U.S. auto industry officially coins the actual term automation. Just a few years later, in 1952, boom, we get the very first prototype numerical control machine. Cut to 2010, and suddenly we're dealing with cloud-based storage and computing. The exponential speed of these recent advancements is honestly just staggering. But you've got to wonder, why push so hard and invest so much capital into this? Well, the primary goals of automation go way beyond just, replacing manual work. Factories are continuously driven to innovate, to integrate complex operations, drastically improve overall productivity, guarantee product quality, eliminate human error, raise personnel safety in hazardous environments, and even economize plant floor space. At the end of the day, it's about powerful economic and safety considerations working hand in hand to keep the products we buy both affordable and reliable. Moving on to Section 2, Hard v. Soft Automation, the Flexibility Dilemma. When designing a production floor, factories essentially have two major pathways they can choose from. Let's put these two pathways head-to-head. Hard automation relies on fixed mechanisms. It's extremely fast and highly specialized, but, and this is a big but, it completely lacks flexibility. It is designed to do one thing perfectly forever. Soft automation, on the other hand, is computer-controlled. It's super adaptable and can be easily reprogrammed to produce complex shapes and entirely different parts without having to build a completely new machine from scratch. To really emphasize the sheer scale of early hard automation, consider this staggering cocktail party fact. By the end of the 1920s, utilizing fixed mass production techniques, Ford Motor Company was producing more than one car per minute. Think about that. One complete automobile rolling off the line every 60 seconds. That is the unmatched raw power of dedicated, hard automated machinery. Just take a look at the immense complexity of this large transfer line used for producing engine blocks. You've got milling, drilling, boring, washing, and testing stations, all seamlessly linked together in this one giant mechanical beast. But while a system like this can easily churn out 100 engine cylinder heads an hour, it completely lacks flexibility. I mean, you can't ask this massive machine to suddenly start making bicycle frames, right? It literally only knows how to make engine blocks. So how do factories actually choose between the two? Well, it fundamentally comes down to production quantities and the specific economics of the operation. If you're making, say, 1 to 10 experimental prototypes, you absolutely use flexible, computer-controlled soft automation. If you're in the batch or high-volume range, 5,000 to 100,000 units, you need slightly more specialized setups. But if you cross into mass production of over 100,000 automobiles or appliances, that massive initial investment in inflexible, hard automation suddenly becomes the most economical choice by far. All right, Section 3, the birth of numerical control, the brains of the machine. This shifts our focus to the how. How do these massive machines actually know what to do without a human guiding their every single move? The answer to that comes from a truly amazing historical anecdote. We literally go from 1800s automatic pianos to 1940s helicopter blades. So an American inventor named J.T. Parsons was trying to machine incredibly complex helicopter parts. He was actually inspired by the pianola, that automatic piano that played music by reading air flowing through holes punched in a paper roll. Well, Parsons had this light bulb moment. He realized he could use perforated paper containing numerical data to control the physical, ultra-precise movements of machine tools. How wild is that? And that brilliant realization gave us the basic steps of numerical control, or NC. Let's break down the technical mechanics of how these instructions physically move the work table. Step 1 is data input, where numerical information is rapidly read and securely stored right in the machine's memory. Step 2 is data processing, where the control unit actively reads and translates those programs. And Step 3 is data output. This is where the processed info is instantly translated into pulsed commands sent to a servo motor, which perfectly moves the work table exactly where the cutting tool needs it to be. Section 4. Open and closed loop systems. Trust but verify. Let's introduce the technical core of modern CNC machines by examining exactly how they verify their own work. You can kind of think of this as doing a task blindfolded versus doing it with your eyes wide open. In an open loop system, the controller sends signals to the motor completely blindly. It just assumes the table moved exactly as commanded, but it never actually checks the final position. In a closed-loop system, however, the machine has its eyes wide open. It uses transducers and sensors to constantly measure and accurately verify the table's exact physical position on the fly. And this brilliantly illustrates the real aha moment of closed-loop systems. It all comes down to one word: feedback. As the rule goes, through feedback control, the position of the work table is compared against the signal, the table movements terminate when the proper coordinates are reached. That feedback loop right there is the fundamental difference between a pretty good machine and a perfectly precise machine. Now, to manage all these complex sequences and feedback loops, we got another massive leap forward in 1968, the Programmable Logic Controller, or PLC. Before PLCs, factories relied on incredibly messy, hardwired mechanical relays and pneumatic switches to coordinate their operations. It was a nightmare. PLCs totally revolutionized the factory floor by replacing all that tangled hardware with clean, reliable software that could coordinate sequences perfectly and be reprogrammed in just a fraction of the time. Which brings us to Section 5, the future of manufacturing, total equipment management. It's time to bring this explainer to the present and look at the future paradigms of automated production. Today we look at automation as this massive integrated ecosystem, which requires total productive equipment management. The main goals here are predictive maintenance, reducing setup and cycle times, maximizing machine utilization, and essentially eliminating product defects altogether. And why this matters to you is actually pretty simple. Managing these highly complex, interconnected machines efficiently is literally the only way modern manufactured goods stay globally affordable. It requires constant teamwork across the entire organization to keep that productivity high. And the absolute cutting edge of that efficiency right now is CNC powered by cloud computing. Modern machines are now equipped with smart sensors that stream massive amounts of data to powerful remote cloud servers in real time. So instead of just following basic onboard code, these remote servers have the processing power to solve highly complex physics models on the fly. They're instantly sending instructions back to the machine to optimize its cuts, speeds, and movements while it is actively working. It's incredible. But, of course, this constant connectivity introduces a brand new, highly controversial dynamic. With heavy machines now actively controlled via the cloud, we have to ask, is the future of manufacturing limitless, or is it a massive cybersecurity risk just waiting to happen? As we increasingly rely on third-party servers and internet tools to run our physical factory floors, the vulnerability of our hyper-connected modern systems is a debate that is really only just beginning. It's definitely a provocative thought to keep in mind the next time you marvel at a perfectly manufactured automated product.